Thank you, Gabor, for the introduction, and to the organizers for having me, and to my mom watching on Zoom, happy birthday. I'm going to be talking about some free boundary Monge-Ampère equations and some applications to both geometric analysis, optimal transport, and some Calabi-Yau and Kähler-Ricci soliton geometry. So I'll give a little bit of an overview and some motivation, and then along the way, I'll try to show how this approach that we have is very general and kind of show the limits of it, because we have a lot of experts in the audience, and I think there'll be a lot of places that can connect to some questions that we still have, which hopefully can interest some people here. So the type of questions we'll be answering are of the form Monge-Ampère, and I'll leave this right-hand side empty for now. So the classical Dirichlet boundary data is prescribing something like u is equal to 0 on the boundary of omega. And we're going to be adding in a second type of boundary equation here, which is that the boundary, that the gradient image of our set is going to be a prescribed P. So you can think about this as part of the seed of our construction is going to be this given one here. Now, what makes this a free boundary equation is that it's right now overdetermined as prescribed. So I'll put in the right-hand side in just a little bit here. Because generally, if you were able to, cover up this Neumann type condition, you'd be able to solve the problem. But similarly, if you also covered up this type of condition, you might be able to solve the problem. So prescribing both means you really have to get lucky on what kind of domain you're looking at. So the flexibility that you have to add is that omega here is not actually prescribed as part of the problem, but is meant to be solved as part of the solution here. I'll talk about where this comes up in a couple different places. So the first one is, of course, from optimal transport. So Monge-Ampère equations generally give solutions to the optimal transport problem with the quadratic cost. So as we're familiar, if you have, your cost function, which I've never written like this, but everyone is doing now, so it's minus x dot y here, then we can solve problems of the form that d squared u of omega is equal to maybe g of x over g prime of nabla u of x is the classical optimal transport problem. And then you have the boundary condition is equal to omega prime. Now, what is the optimal transport problem that we're solving here? It's that we have, two convex domains, omega prime, and maybe we have, g of x dx is our measure here, and then we have g prime of y dy is our measure here, and we're trying to these are both probability measures, let's say. So the classic, the result of Benjy says that this is equivalent to the Monge-Ampère problem here, where exactly this one is given by this optimal transport problem here. So this is just the classical second boundary problem. We haven't yet introduced a free boundary here. One place where the free boundary immediately comes up and from the optimal transport is from a recent work of Fried and Tristan that examines the regularity of these maps. And what they prove is a monotonicity formula saying that when you blow up near the boundary, you get a homogeneous optimal transport map between cones. So understanding the regularity on the interior is given by the theory of Caffarelli and some others. And this boundary behavior is it's a little bit tougher, but this gives the first place where you can solve it, for example, in 2 dimensions here. The second place where this comes up is in the theory of Calabi-Yau manifolds, in particular solving for some of these Tian-Yau metrics that many people before have already talked about. So I won't go into too much depth there, but a particular equation of exactly this form arises when you're looking at the complement of an anti-canonical divisor that has multiple sections here. So this, the result of Tristan and Yang Li was in the case where you have, a divisor that splits into 2 components with a simple normal crossing that are rationally equivalent. That reduced to a free boundary ODE, which can be solved quite explicitly. And that flavor of problems from the PDE was also expanded by Tristan, Fried, and Yau in addition. So that solved some other free boundary problems that arise in that context there. So before I get into setting up how one can approach and solve these problems, I want to just give a little bit of both applications of it and write down the specific nature of the problem that we're solving here. So I'm going to write down a very general family, and then I'll explain how we can use these different levers to set up different equations here. So I just want to get my notation correct. So there's going to be a piece of it that's going to be connected to the function, and then there's also going to be a Legendre dual component and a gradient component here. Okay. So the reason, we have three different parameters, but you can think about each one of these as a different type of lever you have to set up an equation that you'd like. So particularly setting up any one of these equal to, one kind of, zeros removes them, and you can look at some simple ones. So, the Monge-Ampère eigenvalue equation would just be like f is to the a polynomial. Some of the free boundary ones have g as a polynomial. Too. So you can think about the input data here is not just this P here. Maybe you can think about this as some sort of polytope of a moment map, but it comes endowed with this measure, h of y dy. So this is like your part of your initial data that you want to solve. Okay. So yeah, let me first talk about some of the different applications of this. So the first one here is if you have g equals h equals 1, and then you have f of s is equal to s to the n, you get the Monge-Ampère eigenvalue problem here. So there's a lot of really wonderful results on this in the classical setting where it can be given a variational framework. So one particularly beautiful result is due to Savin and Namle, saying that in the case here you can really understand the full regularity of the solutions of this given by the boundary. In fact, that you really do get the optimal boundary regularity in the classical Dirichlet setting when you're solving the eigenvalue problem here. Now, the trade-off then, of course, is you don't really know necessarily what the gradient image is there. So if you want to solve the reverse type of problem here, the trade-off now is that we don't know the domain that we're solving the problem on here. So the regularity, that even though it's very, very well understood in the classical Dirichlet setting, when we move into this free boundary setting, it's a little bit more mysterious. So one can think about, the types of problems that occur when you take you look at P and you get some domain omega and try to understand what can occur. So in particular, P could be quite singular, like it could be a polytope or a simplex, and then you won't get the maximum regularity that you assume. But maybe some iteration of this process shows that there is like a smoothing effect that happens there. The other thing about the eigenvalue problem here is that, and I'll talk a little bit more about this later, is that we'll get some quite strong uniqueness results. In this case here, we're actually going to show that in this setting, when you have, this g function doesn't appear, generally you get that this function will be convex. So, the minimizer, the solutions to this will be unique up to some symmetries of the problem, meaning that anything you get can actually be thought of as a convex, as some sort of invariant of any part of the initial data, whether that be P or omega. So you can get some some reconstruction type results of that variety there. Similarly, you can do a lot of other types of equations here. So, any type of polynomial here is going to give you the same one. So you can solve these more general eigenvalue problems where you have f of s equal s to the k. And now this one doesn't have the same homogeneity that the eigenvalue has, but structurally it has other similar properties that you get. And similarly here, if you keep G1, but you could add in some sort of density H, which it's quite flexible what you can put in there, depending on what regularity you want to get on the interior here. So the standard properties that you would like for H to apply the Caffarelli theorem are things like doubling and understanding its vanishing order. But aside from that, it's quite flexible. Okay. So another problem that fits into this framework that's very relevant here is Kähler-Ricci solitons. So if you want to solve a problem that d squared u is equal to e to the minus u, and then nabla u of Rn is equal to P. So now here, when P is given by the moment polytope of a toric log Fano variety, this gives you the Kähler-Einstein equation here. In particular, there's generally an obstruction to get the Kähler-Einstein one, which is that you want this polytope here to be centered at the origin. And generally, we will see that that is an obstruction to solving many of these problems here in the convex setting. Otherwise, there's a weight that you can put on, which is available from this measure on P, and that instead introduces from the Einstein setting to the Kähler-Ricci soliton setting here. So these ones were solved by Berman and Bernsen, and this gives a really nice characterization of the toric Kähler-Einstein setting. In particular, you can compute like the Futaki invariance in a much more simple way than the general K-stability framework here. So now the difference between this equation now is that we're no longer solving this equation on the entire domain Rn, but we're just looking at the place where u is 0. So what instead this produces is something that can look of the form reach of omega is equal to omega on some region x inside your variety, but then your omega to the n is going to be 0 outside. So here you're going to have like some singular part here. Now, one of the reasons this is a nice example of this because it's one of the kind of critical aspects of this equation here. So in particular, there's this constant lambda here, which generally you can kind of ignore or reset to 1 under most tame cases. But there are certain cases where that constant becomes quite critical. And that is related to the growth rates of these two parameters, f and g. And I'll explain a little bit more about that later. But in this case here, what you really want is like log of f, and you want to compare that to the integral of g. So let's just write, log f of s compared to s in this case. So now, when their function is the exponential, these are actually comparable to each other. There's going to be a competition between these two terms here. There's going to be a limit slope that comes up. And lambda is going to be prescribing that limit slope in some ways, which means if you have log f minus s, if you don't necessarily put a coefficient in front of here, you might not actually get a solution. And that does occur in this case here. So there is, some type of obstruction on what kind of what problems you can solve here as you change that constant versus in other problems like this Monge-Ampère eigenvalue, you can just rescale it away. So in this case in particular, one can imagine that that constant is actually related to the size of the set on which you're solving the Kähler-Einstein equation, because we know we can solve it on the whole domain Rn. That's the classical, that's the Berman and Bernsen result. So this free boundary one can imagine you expand it as you change that constant too. So it would be an interesting question to think about how that works there. Here. So another aspect that comes up in classical Monge-Ampère, I won't talk too much about this because it's not as thematically aligned with this conference, is a Minkowski problem. So the real Monge-Ampère equation comes up, in these toric cases in the Calabi-Yau case, but the real Monge-Ampère equation as a curvature quantity is the Gauss curvature in standard n-dimensional real space instead of complex space here. So the standard Minkowski problem says if you have, some sphere and we're going to put a measure on it, can we find some, convex sphere such that its Gauss curvature at every point here, you can just map by the normal, is given by some function h. So in this free boundary context, this, you can think now we're going to be taking the graph of this function, and that's going to give us, some affine surface. And it's going to be the graph function of it is going to be like an affine an affine sphere. And now you can take its normal, and it's going to be some convex set here, and it's going to have some Gauss curvature. So the question is, can you prescribe that in solving this equation is doing precisely these types of equations. So just like in the normal Minkowski problem, well, by the Gauss-Bonnet formula, if you integrate the Gauss curvature, you get a topological obstruction quantity. So that means, there has to be some balancing or integral condition. You can just think about that as a divergence type equation here. And the same exact thing here will happen too, which is that there's some barycenter you can either think about it of the prescribed density that you're putting on the sphere. But morally, you should also think if we're looking at this plane and we want to take a graph over it, it would be very difficult or impossible to take a convex function over it that points in this direction. So you can think about if you put this density on the sphere, there's going to be exactly like one plane direction that's kind of like the average of all that curvature, and you would need your affine sphere to point in that direction. Otherwise, you won't be able to satisfy this divergence theorem type equation. And lastly, I'll talk a little bit more about this optimal transport problem. So very related to the Calabi-Yau one. You can use equations like this to create optimal transport maps between cones. In particular here, we'll see what the obstruction is, but one thing that happens is, allowing G to have sufficient growth is really one of the levers that enables this solution to exist. And what that's going to correspond to in the optimal transport setting is a sufficient density on your cones here. So in this case, the original, the problem that arises from different, settings of different quantities of divisors appears in, the previous works of Tristan, Fried, and Yau that I mentioned. But in this one, you can produce optimal transport maps that lie into a half space, provided that the density on that half space is sufficiently high, which gives you a little bit more wiggle room in order to do it here. So what the problem here actually is looking like is that this link of this cone here is P. So that's where you're going to set up this equation. And this equation just naturally emerges by looking at this, infinite mass optimal transport problem. But when you put the homogeneity on it, it reduces to this compact link problem here. Okay, so you can just, if the map is given by nabla phi, the equation is going to be something like this. So here, this beta and this alpha are your degeneracies, and you need beta to be larger than alpha, strictly so, in order to get the existence here. So I'll talk a little bit about so this setup was in a paper that was with Tristan Collins, and then in a follow-up result, there is a more general optimal transport problem that you can solve between two cones. So this is joint with Collins and Fried as well. Here when you remove the half space, you now introduce some sort of second boundary condition here. So now no longer the condition is going to be u is equal to 0, but it's going to be u plus some support function is equal to 0 on the boundary of omega, where now this can be thought of as, there's a second sort of link here. And now you want this is your new Dirichlet boundary condition. So we can think about, before we were looking at the graph over planes, and now we're going to be looking at the graph over this cone sigma. And that's why your target is no longer going to be flat, but it's going to be tilted up by this point here. But now without this density type equation that's going to occur here, you need some other mechanism to allow the existence. And there's this acute condition here, which completely removes some of this invariance and these bad directions that we'll talk a little bit about more. So in this one, if you allow some type of condition here where sigma and p satisfy a geometric relation, which we call obliqueness, you're also able to solve these types of optimal transport problems, and presumably a much more general family as well without some of the obstructions there. Okay. So now I'll just get a little bit into talking about how one goes about solving and setting up free boundary problems. In general, solving the free boundary condition, there are various different ways one can approach it, and there are many different types of free boundary problems as well. So one can maybe think about, the most linear problem would be something like the Sarin problem, which is the same equation, but now you want to satisfy the Laplace equation. Related to that is the Bernoulli equations, which come in a family of things. So that was studied by Alt-Caffarelli, and there's a generalized family called the Alt-Phillips family, where you satisfy a functional. There are also, ODE techniques, and ODEs, when you have free boundary ODEs, you can generally use existence and uniqueness to kind of just guess the types of answers that you can get for a shooting problem. So there's lots of techniques there that arise in geometric analysis, studying things like minimal surfaces or capillary surfaces in different phenomena. So generally, symmetry is one of your best friends in approaching this. And then the other main method you have to use is just set up the right functional and show some type of estimate and do it. And so in this case, we don't want to assume any types of extra symmetry, so we will be looking at the functionals here. So the main ingredients of this optimal transport problem are to look at the two sides of the equations and kind of separate them out. One side is your p side here, so we'll call that like the target, and then this omega will be, your domain side here. And this equation actually splits that, so everything we can see here really lies on either the original side or the Legendre dual side. So that's why the Legendre dual and the gradient image are like fundamentally on the other side here. So we should think about these two pieces as together, and this F1 is together here. So we'll create a functional that independently produces variations that will have both of these parts here. So you define capital S to be the integral of little f from 0, and similarly, capital G to be the integral of little g. Now, the function space that you want to look at here is the first one is going to be I of V. So we'll say V is a convex function on P, and it's going to be greater than a positive function here. So I of V is going to be on the Legendre side here. So this one is going to be given by the integral over Rn of F of the Legendre transform. And now we're going to do the indicator function just on when this is less than 0, dx here. Okay, so this is just chosen so that when you take the variation of it, you're going to get exactly this f part here too. So now on the other side, the functional will be a little bit more complicated, but morally it's going to be very much the same. There is a little, so I'll write J of V here is going to be, so G inverse of the 1 over H times the integral over P of G of V and then H of Y dy. Okay, so this is our natural measure on P. H is just making it a probability measure here, and now G is this integral of that. So this says that we should be putting, we want G to be monotonic and in the direction. So the important pieces of this functional are we want to put some convexity and concavity on both of these here. So the right notion is that if f is log concave, we will take minus log I as the first piece of our function, and then we'll add in lambda j as the second. So this is going to be our total energy function is given by that. So generally speaking, we're splitting this up into a convex piece and a concave piece, and I'll give you a little bit more details on the types of properties that we need to discuss for both of these here. And there is this kind of borderline case where if you let G just be the identity, so little g is just a constant, this one here is not going to be concave anymore, but it'll be just like linear. So this is actually switches to just the convex setting. So in these are the cases like that appear in the eigenvalue problem or the Minkowski one here, or the Kähler-Einstein setting in that case where we encounter an obstruction. In the case where this one is concave, it's mildly, what we'll show here is that we can kind of separate these directions into a finite dimensional piece of concave directions over which we can maximize something and then minimize, meaning that it's convex and concave, but kind of in a product-like structure, meaning that you can do a mountain pass argument, and that's going to generally be the strategy here. So in that case, the coercivity of the function is going to come from this J side here. And what we'll find is that there's going to be like some type of blow up behavior as you go in any direction, which will force your free boundary to be somewhat normalized here.
Is that capital H in the denominator for the integral?
Yeah, exactly. This is just just to make this a probability measure. We just want to apply Jensen's theorem on this here. All right. Any more questions? Feel free to interrupt. Yeah. So there are two basic behaviors that can happen and really affect the equation here. So and they're kind of both invariances of these different problems that you want to remove. So the first one is like a translational invariance, and that just comes from this I piece here. So this is invariant under translation. So translation on this free boundary side here, we can see if we define this to be omega, so it's like omega moves to omega minus some x naught. Nothing's going to change on this I integral side, but we can compute what this looks like from the Legendre definition here. So this corresponds to changing your function v by an affine piece here. Maybe this one's a plus, I think, like this. So this shows this is exactly where the obstruction comes in, because now if we were to have a critical point, that means that this function is not going to change along any of these variations here, but now this one will. So what that tells you here is that this integral of g of v minus y x naught, and let's do the case here where g is just the identity, dy h of y dy. This must vanish for all points x naught that are admissible. And this is the barycenter condition. So the only way that this can happen is if P has its H barycenter at the origin. Okay. So it's just a nice way of saying that this functional picks out a natural choice of representative for this eigenvalue problem. You can think about, if I move this domain omega, I'm not going to change the gradient image, and the right-hand side doesn't depend on the point. So we need to just put its barycenter at the origin. So this functional naturally picks that out. And similarly, if you were to write this out for the Minkowski problem, you would see this condition as well. So the other, so we'll call this like the convex case here. So maybe we'll separate out. So when little g is equal to a constant, E is going to be convex. So in this case, we get a barycenter obstruction. We can also, for those who are familiar with the Kähler-Einstein setting, see that if you took this to be the moment polytope and set up the Kähler-Einstein equation here, there would be exactly one linear function that you want to do to put its barycenter at the origin, and that corresponds to turning you from a Kähler-Einstein into a Kähler-Ricci soliton. It gives you the directions of the vector field there. So you're not Kähler-Einstein, but you are a Kähler-Ricci soliton here. Okay, and then the second type of bad behaviors that can occur is a rescaling. type thing here. So when you rescale a function v on your domain P, that's going to be changing its gradient image. So you can think about that as the free boundary is becoming larger and larger. So that's going to occur in the other case. We want to really understand that. So this will be, we'll call this, the H1 condition. And then there's the concave condition. We really want some blow up behavior here, which is going to be a coercive piece of the functional estimate that occurs later on. And that's just going to be, you can think about it from, so now we'll set G, there's going to be two cases here. I'm not going to talk about all the details of the different things that we can show. The admissible triplets or the admissible pairs of F and G, there's a lot of different cases that can occur. Morally, they're all about the relative growth rates, and we wanted to show as much of the places where the techniques will apply. But we should really just think about what matters is the asymptotic comparison between F and G here. So there's two cases here. So either if G has a finite upper integral, we'll say G of infinity is equal to 0. Otherwise, we'll just set G of 1 equal to 0. If it blows up in both directions. But the real key piece that we want is this criticality equation that G of S times S to the n minus 1 is going to be minus infinity here. And what this is going to correspond to here is some blow up limit that as you take these different scaling and non-compact shiftness, it will behave very, very badly for the energy. This will create this min-max procedure here that we can always get rid of. And so this condition here, if you were to make G just some increasing things, you would still have a convex function. But your barycenter condition would no longer be the right one because you can think about we'd be putting some convex function here instead of just this being the linear one. So there would be there probably would be some appropriate condition there, which is not exactly a barycenter, but it would relate quite subtly on the geometry of P and the particular function you chose. In this borderline, convex and concave case, it's precisely this barycenter condition, which is easy to write down, but otherwise it's going to be highly nonlinear. And you can probably if you take certain P and a different like increasing convex G there, it's easy to construct examples of a function V where this is going to be like minimized with its infimum at the boundary, and we'll see why that's important as we go through this. But when you have V, if it's infimum at the boundary, that's saying like there's like a negative direction later on. So that's going to correspond to its free boundary having the origin on it. So its polar dual is going to blow up. And this is also a source of non-compactness. It's kind of mesh quantifying the molar volume of the free boundary here. So yeah, no, it's the nonlinear condition is really delicate outside of that here. But in this condition, we're going to need this, and then there's going to be a relative growth rate. Of F and G. As I said before, like, we're going to be comparing log F and G and really trying to understand it here. So let me just paint a picture about like how we want to do this type of strategy here and what are the ultimate objects that you need to show are the degenerations that can lead to, bad energy functionals here. So we can call it, if you have so I'll do it on the free boundary side here. So this will be like in the X variables here. So if you had some function here, which is very long and skinny, so this domain here is going to be omega. If we think about the integral I was equal to the integral over omega of F of minus U dx. So what the problem with this type of region is maybe F is, roughly epsilon, but the volume of omega could be, equal to 1 over epsilon. So we have this degenerating family that is keeping this function constant. So there's no way you could hope to extract a limit if this was, somehow not ruled out by the functional. And this example here, it's very easy to construct such a thing that even satisfies your boundary condition. So you just want these outside gradient images to be exactly P. So if you take the convex support function, so the convex support function is just given by the cone function here, where in each direction, this is the gradient image of P. So if we take this convex support function and we subtract a huge amount from it, so this now function here is phi P minus some large constant C, and then we just cut it off at a height, let me call this delta, you get this infinite family of enemies like this. And well, you know, in the limit, this function would be converting to zero. So if you take any minimizing sequence, if this type of behavior was allowed, you could never expect to find a solution here. So you need to rule this type of equation out. But now we're seeing that, you know, we can always arrange this to be on the I side, which means it's going to occur exactly from the J side. Now that condition, the fact that that is going to blow up, is going to be given exactly by these two criteria here as well. Okay. So this example here, it's kind of like the worst case behavior you could expect. Obviously, you know, omega is kind of, you know, getting large in every possible direction here, but one could also imagine it's doing so in only a few eccentric directions and not everywhere simultaneously. Getting this boundary condition is generally quite easy because as long as so you can think about the function space on the other side, every u, you just want its gradient image to be compared to p, it has to lie inside it. So every u is always going to be have some sort of containment like this. So in particular, omega will always be compact. That's never going to be an issue, but you don't know this C is dependent very much on the equation here. So it really needs to be ruled out. So from that picture, this estimate of just measuring, you know, what is the smallest amount here times the size of omega, it's actually a very good estimate on I. It's tight. You can get a bound on it both ways. So we can think of I is roughly like the size of omega times the smallest possible u value here. So that's going to be the inf of u. U is negative here. Okay. And it's f of the inf of u here. Now the J function is, again, that one is much more difficult to write down every case because we want to allow for the maximum flexibility here. But essentially, you want to use a coarea type estimate and get a very similar thing. So what happens you need to look at is as you approach these enemies, what is occurring on your free boundary and how can you show that the J functional is somehow blowing up? And if you can do that, then you can minimize it. And we'll actually sorry, I think I have it. You want to maximize that. That's the concave piece. And once you've maximized it with respect to some sort of these tilting maps here, you can minimize the entire thing there. Okay. So from the structural properties of J, you can really write, so I'll write G of J everywhere because it had this inverse property here. Morally, you should think about this as some sort of quantity that is given by like the inf of v times inf v to the n over omega. So this is the final bound that you're going to get on it. But really, what we're looking for is we're integrating over p this g of v. So what you want to find here is this is going to be extremized by the infimum value here. But this one was extremized by the infimum of u. So these are two different quantities that are related by the Legendre transform, but not exactly. So this inf of u is related to v of 0. So the problem here is what if v of 0 and the infimum of v are very different values here? And that's why that can't occur unless they're very far away from each other. So the real damaging case is when you have an infimum approaching the boundary. Now, you can always construct such a thing by just subtracting off your supporting hyperplanes, which is exactly what we saw in this barycenter condition here as the piece that we needed to avoid and manually do. Okay, so what you find is exactly from an estimate like this, when you're maximizing over these types of representatives, you get that the infimum of V is comparable to V of 0, here, like that. And this is going to occur always in a special translated case when omega is centered at the origin here. And you can think about it as if you put your John ellipsoid or some balancing, what can be very bad is if the origin is very close to the boundary of omega. Now, this condition here, you can think about this also in this oblique case as given for free by the geometry. So the oblique condition, what it says is that when you take the free boundary side, so now we were looking at this function u plus phi sigma circ. So let's call this function w. This is the natural object that we had in this oblique condition here. W at any point that was not the origin was uniformly increasing fastest. So if we think about, the domain here, so if this is the graph of W, we had the oblique condition gives you two strict cones that your W function must lie between, which means that you have some inner radius and outer radius where your free boundary is controlled over. So this normalization procedure for the oblique case actually gives you all these estimates for free, which is why you don't need any more of this condition. So there's a trade-off here between the geometric properties that you're allowed the geometric properties you must assume, or the types of right-hand side in the equations you're allowed to do. Okay. So the final estimate you can kind of show is going to be of the order E is going to be greater than or equal to minus log f of x plus, let's say, lambda x here. And now it's very clear why we wanted to compare the asymptotic rate of log f and g. There's a g hidden amongst here that from these structural conditions like that. And when this is uniformly minimized, or when there's a lower bound on this, so if like f was any type of polynomial, or if it was exponential and you choose lambda sufficiently large, then there's an exact minimum. And when that happens, what it tells you is that all of these bad behaviors are under control. So you don't have a free boundary diverging. So the size of omega is going to be controlled. And you don't have, V of 0 becoming too small. What does that give you? It's now those are exactly what you need to take a decreasing limit and be able to apply Arzela-Ascoli. So now you can take some V going to V min, and this will be an Alexandrov solution. To do this step, of course, you want to show that this you need to upgrade your solution to an actual Monge-Ampère one, and this is the results of McCann, who I think he left, and Gangbo McCann show that these optimal transport problems can be reframed exactly in the Monge-Ampère setting. So this you can extract this Alexandrov solution as a weak solution to this, and then if you have good properties on your initial measure H of P, you can use the Caffarelli theory. So there's a lot of loosenings that you could do to get the best regularity theory on the interior. Morally, if your regularity of H, let's say it's going to be positive everywhere, and doubling will control the regularity of your final solution from this procedure here. So I think that's about my time.